So this is the continuation of part 1 of my t-SNE tutorial. So in part 1 I ended with the drawbacks in SNE and what type of novel features that t-SNE has. And now I'll go through for each of these novel features much more thoroughly. So the first improvement in t-SNE is that it uses symmetric version of the similarity, which is named symmetric SNE. So the main feature in symmetric SNE is that Pij is equal to Pji. And if you are comparing 2 points, the exact same points, Pii and Qii, it's going to be 0. So what you can see is that there's no I given j because you make the assumption that they are symmetric. So Pi given j and Pj given I are going to be very similar. So this is the low dimensional representation. It's exact same as the previous one, but we don't have the conditional here. And then this is Pij is going to be the high dimensional representation of the difference or the similarity in data points. And then this is going to be the gradient function. So instead of having 2 in here with the conditionals, we have 4 times the summation of difference between Pji and Qji times yi minus yj. So the second main improvement in t-SNE, like I said, is this t-SNE mapping, where the low-dimensional data points are represented as t-distributed instead of normally distributed. So in t-SNE, a student t-distribution with 1 degree of freedom, which is a Cauchy distribution, is used to represent the low-dimensional map. So the low-dimensional map is represented by Qij, and as you can see here, there's no exponent, and this representation looks very similar to a kernel of a t-distribution. So the main reason why t-distribution is used is that t-distribution is robust to outliers, and unlike the Gaussian distribution, it doesn't have exponent in it, so it's faster to evaluate. So in Gaussian distribution or the normal distribution, in the kernel you have exponent, and then inside that you have the difference and divide by the variance. But doing all the calculation might be computationally costly, so choosing a student t-distribution is much faster. And then the gradient of the cost function via the KL divergence is going to look something like this. So you have very similar or the exact version of the cost function, the gradient of the cost function in the symmetric SNE, but in addition to that you also have this additional term. So far we have looked at how t-SNE is different than SNE, and then I'm going to go through step by step what the t-SNE algorithm is doing. So the general idea of the t-SNE algorithm is that you have a data set with data points having very high dimensionality. So you have data set X with data point x1, x2 through xn, each of these points with very high dimension. And then you have a cost function parameter, which is the perplexity or the perp, and the perplexity is associated with the variance sigma in the cost function. And then you also have optimization parameters, the number of iteration t, the learning rate eta, and the momentum alpha of t. So you have all these components, the data, the cost function parameters, the optimization parameters, and then you use all of them to get the lower dimensional representation y. So here's the step-by-step process of the t-SNE algorithm. So you start with pairwise affinities pj given I in the high dimensional map with the given perplexity perp. And then you set Pij equal to Pi given j plus Pj given I divided by 2n. So the n is going to be the number of data points. And then you sample initial solution for the y at the 0th iteration for y1, y2 through yn from a normal distribution with the mean 0 and variance 10 to the minus 4. And so essentially you sample from a normal distribution with mean 0 and a very small variance. And the I here represent the identity matrix. So if you have n number of data points, it's going to be an n by n identity matrix. And then you start the iteration. So for t equals 1 to t to capital T, which is the maximum number of iteration, first you compute the lower dimensional affinities Qij. So in the first iteration, you will calculate it through the initial solution, which you sample from a normal distribution. And then you compute the gradient delta C divided by delta Y, which is through the KL divergence. And then you use the gradient descent formula to get the solution at the tth iteration. Okay, so you iterate through all these processes until you hit the maximum number of iterations, or until you converge to the asymptotic point of the solution. So this is the basic idea of the t-SNE algorithm, but there are also modifications in order to make things faster, using Barnes-Hut approximation and all those different very sophisticated methodology. So the t-SNE is a very popular method. So it's been implemented in various languages and software packages, and I will go through a few of them here. So there's a package called t-SNE in R, and then the main function is just t-SNE. So you provide the data set, the high dimensional data set, the k, the number of lower level dimensions, the perplexity, and then the maximum number of iterations. And then after that it will provide this lower level representation Qi after a certain number of iterations. And then there's also an implementation in Python via sklearn module, sklearn.manifold.tsne, and in that specific function there are arguments including number of components, essentially how many number of dimensions you need, the perplexity, the learning rate, and also the maximum number of iterations. There's also an implementation in Julia with the module t-SNE, and it also takes very similar argument as that in other software packages. And finally, there's also implementation in MATLAB via t-SNE function. And for that function, the input arguments are going to be the dataset X. And you can provide the labels if you already know it. So if you have a supervised clustering data, then you can provide the label. The number of dimension expected in the lower level manifold. So it's usually going to be 3 or 2 so that you can visualize it. And then initial dimension, which is going to be the initial number of dimensions in the data, and also perplexity. So t-SNE has been very well received by the community, but there are also some criticisms against t-SNE. And there's this great paper by Wattenberg and Villegas and Johnson. So Wattenberg and Villegas are big names in Google Brain project, and Johnson is works in the Google Cloud project, and they recently published a paper called How to Use t-SNE Effectively. And it explains some of the drawbacks of t-SNE with some interactive visualization tools. So when you read the paper, you can also use this visualization tools, and you can change the parameters and see how t-SNE results change. And in here, I will go through some of the criticisms that they mention um, about t-SNE, but I would highly recommend you to read the paper yourself, and also use the visualization tool. So the first one is that different perplexity can lead to completely different clusters. So this perplexity measure is what I told earlier, where it loosely interpreted as the number of neighbors of a certain point. And in the original papers, the authors say that you can pick a perplexity between 5 and 50, which is the optimal. And in that range, it's going to be very robust. But in this paper, How to Use t-SNE Effectively, they mentioned that if you choose a perplexity that is too small, then the local variations are going to dominate. And if you choose a perplexity that is too large, then the global changes are going to dominate. So you have to be careful what perplexity you choose. And then another one is that cluster size doesn't have any meaning to it. So in principal component analysis, the axes have very good interpretation. So the y-axis is going to be the direction where the highest variance explained, and the y-axis is going to be the direction where the second highest variance explained. But t-SNE doesn't have that intrinsic interpretation. And it also has the tendency to expand dense clusters and contract sparse clusters. So if you see a dense cluster, that doesn't mean that cluster points have very small variance. Or if you see a very large cluster, that doesn't mean those points have very large within cluster variance. And then another criticism is that the distance between clusters might not have clear interpretation. So if you have two clusters that are close to each other, and there are another two clusters that are far apart, just because of the cluster intercluster distance, that doesn't mean those clusters that are far apart are very different from each other, or clusters that are close enough are very similar to each other. And then finally, in this paper, they also mention sometimes if you provide random noise as the data, then t-SNE can lead to false positive structure, when in reality there is no structure in this random noise. So you have to be careful in terms of how you use t-SNE, how you choose the parameters, and also how you interpret whatever the results you get. So in summary, t-SNE is an incredibly useful tool for clustering and data visualization, and it provides better structure for very high dimensional data. It is very highly flexible, but for that same reason, it also leads to other drawback in terms of the lack of interpretability. And finally, also not very intuitive to tune the parameters like perplexity, the number of iterations, and the tolerance for convergence and other parameters. So if you are interested in using t-SNE and want to learn more about it, I would highly recommend reading the original paper by Lawrence van der Maten and Jeffrey Hinton, and also this recent paper called How to Use t-SNE Effectively, to understand how to construct t-SNE, and how, when you get the results, how to understand it and interpret it. I hope you found this tutorials useful, and thank you.